A radar screen aboard a guided missile destroyer lights up. Somewhere over the horizon, a launch event has just occurred. The system calculates approach trajectory, speed, and the one variable that defines everything that happens next: time to impact. 90 seconds, just 90 seconds. That number sounds like enough? It isn't. Here's what most people assume when they picture an aircraft carrier strike group defending itself. They imagine something like a video game. Threat appears, system detects it, interceptor fires, problem solved. The carrier is safe because it costs $13 billion and carries the most advanced defensive radar ever put to sea. That assumption is built on a misunderstanding of physics, and physics doesn't care about price tags. Today, we're going to break down exactly what happens inside those 90 seconds. The engineering of the attack, the engineering of the defense, and the precise physical reason why the most expensive defensive system ever floated faces a problem it has not yet solved. There is one specific moment in the kill chain where the math stops working, one specific physical phenomenon that changes everything. We'll get to exactly what that is. But to understand it, we first need to understand how a ballistic missile and a carrier defense system actually work from first principles. Let's start with the missile. The Fattah 1 is Iran's domestically produced medium-range ballistic missile, assessed by Western analysts as the most technically sophisticated warhead delivery system in Iran's current inventory. Iran describes it as hypersonic. The more precise classification is a ballistic missile with a maneuverable re-entry vehicle, and that distinction matters enormously for why it's difficult to intercept. The first stage is a solid fuel booster. Solid fuel is critical for one operational reason: almost no preparation time. A liquid-fueled missile must be transported, erected, and fueled at the launch site, a process taking hours and producing a huge infrared signature detectable by satellite. Solid fuel is already in the motor. The launcher drives to position, erects, and fires in minutes. By the time a surveillance system processes the thermal plume, the first stage has already burned out. The missile climbs steeply. It reaches an apogee near 300 kilometers altitude, essentially vacuum. The booster burns out. And here is where the Fattah does something most ballistic missiles do not. The warhead separates from the booster, but the warhead is not a passive object. Inside the re-entry vehicle is a second propulsion element, a solid fuel post-boost motor, which ignites after separation. This motor performs two completely separate functions simultaneously. First, it accelerates the warhead during terminal descent, maintaining hypersonic speed through atmospheric re-entry that would otherwise slow it through drag. Second, it fires lateral burns, using combined thrust vector control through a movable nozzle and aerodynamic fin deflection that continuously shift the warhead's predicted ground impact point throughout the final 100 kilometers. That second function is the engineering detail that keeps missile defense planners awake. A conventional ballistic missile follows a predictable arc. After the booster burns out, it is a cannonball. A radar tracking it can calculate where it will land with high mathematical confidence from the first seconds of observation. The fire control computer solves the intercept geometry and launches a defensive missile on a calculated trajectory to meet the incoming warhead at a predicted point in space. This is the fundamental principle behind every ballistic missile defense system ever built: the Patriot, the Arrow, the SM-3, the THAAD. You calculate where the threat will be. You put your interceptor there first. The Fattah's post-boost motor makes that calculation unsolvable with confidence. Because the warhead continuously moves its predicted impact point throughout the terminal phase, the fire control computer cannot lock onto a stable intercept geometry. The interceptor assigned to kill it, the SM-6, the U.S. Navy's primary terminal phase defense asset, is a hit-to-kill weapon. It carries no warhead. It wins by being in the exact same piece of sky as the incoming warhead at the exact same millisecond. To do that, it steers toward a continuously computed predicted intercept point. As that point moves, the interceptor must divert, fire its own attitude control thrusters to change course. Each divert costs fuel. The SM-6 has a finite divert budget. The Fattah's motor is engineered to exhaust that divert budget before the intercept can be achieved. This is not a speed race. It is a fuel budget calculation, deliberately engineered to win. But there is a problem that arrives even earlier in the engagement sequence, the one that the maneuver problem is designed to exploit. Plasma. When any object enters the atmosphere at hypersonic speeds, the air in front of it cannot move out of the way fast enough. Instead of deflecting around the vehicle, air molecules compress and heat through ram compression. At Mach 5, temperatures at the vehicle's leading edge can exceed 1,000 degrees Celsius. At the terminal speeds of the Fattah's re-entry vehicle, Iran claims Mach 13, Western analysts assess a genuinely high hypersonic terminal speed. Temperatures can exceed 2,000 degrees. At those temperatures, the air itself ionizes. Individual electrons are stripped from air molecules. The gas transitions from a neutral state into plasma, electrically conductive, fourth state of matter. And here is what plasma does to radar. Radar works by transmitting a pulse of electromagnetic energy, having it reflect off a target, and receiving the echo. This works because electromagnetic radiation travels freely through air, but plasma absorbs and scatters electromagnetic radiation, enough to degrade the return signal, enough to introduce noise and uncertainty into the tracking solution. During the Fattah's terminal descent, the warhead is surrounded by a sheath of ionized gas that attenuates the radar pulse before it reaches the vehicle's skin and attenuates the echo before it returns to the antenna. Radar blackout. For a critical period during terminal descent, the warhead's radar cross-section becomes unpredictable. Tracking quality degrades. The fire control solution, already fighting the continuously shifting aim point, is now also fighting signal noise from ionized air. Two simultaneous layers of mathematical stress during the shortest and most time-compressed portion of the engagement, and those 90 seconds are running out. Now let's examine what the Aegis system is trying to do inside that window, because the engineering of the defense is as remarkable as the engineering of the offense. The Arleigh-Burke-class destroyer carries the Aegis combat system, an integrated radar, computer, and weapons architecture representing the most sophisticated naval air defense ever deployed. The AN/SPY-1D phased array radar simultaneously tracks hundreds of airborne objects across a 360-degree sphere at ranges exceeding 500 kilometers. It is not a rotating antenna. It is a fixed array of thousands of electronically steered antenna elements capable of searching, tracking, and targeting multiple objects simultaneously across different directions and ranges. The computational backbone processes all of this in real time, feeding a fire control system maintaining engagement tracks on dozens of targets at once. On paper, overwhelming. In practice, against a maneuvering re-entry vehicle at hypersonic speed surrounded by plasma, it faces three sequential problems. First, detection and track quality, degraded by the plasma sheath. Second, firing solution stability, continuously disrupted by the post-boost motor's lateral burns. Third, the engagement window itself, compressing as the warhead accelerates into denser atmosphere. All three happening simultaneously in 90 seconds. The SM-6 reaches approximately Mach 3.5. The incoming re-entry vehicle is moving at Mach 10 or above in the terminal phase. The intercept geometry requires the SM-6 to be launched ahead of the target on a converging course, which requires knowing with confidence where the warhead will be. The maneuver problem is specifically designed to prevent that confidence. But there is a layer deeper than the single missile problem, because a carrier strike group doesn't defend against one missile at a time. And Arleigh-Burke carries 96 vertical launch system cells, loaded before deployment with a mix of SM-2, SM-3, SM-6, Tomahawks, and other munitions. Each SM-6 round used against an incoming threat is one less available for the next threat. At sea, there is no reload. The VLS cannot be replenished from a supply vessel. A destroyer that has fired half its interceptor magazine is defending the carrier with half the capacity it started with. The physics of this constraint interacts with the Fattah's engineering in a way that appears deliberate. An adversary operating a layered missile inventory has a structural incentive to sequence cheaper, lower capability threats first, not because they will penetrate, but because intercepting them costs interceptors. Each cheap drone or older ballistic missile that forces an Aegis intercept is reducing the magazine available for the engagement that actually matters. The Fattah at the end of the sequence faces a depleted defender, and the mathematics of that exchange are extreme. A $20,000 drone forces a $4 to $6 million SM-6 response. A salvo of 20 drones costs roughly $400,000 to launch. Defending against it costs $80 to $120 million from the VLS cells, and those cells don't refill until the ship returns to port. The engineering of the carrier's defense was not designed for this math. It was designed for a world where each defensive round was matched against a genuine high-end threat. The attacker also spent significantly per attack. The economics balanced. What changed is the advent of mass low-cost one-way attack systems as the primary volume layer of a doctrine built to exhaust the magazine before launching the penetrating system at the end. Now consider how that engagement window actually feels from the inside of a destroyer combat information center. The SPY-1D radar is pinging. The tracks are live. The fire control officer is watching a threat symbol on a screen that is moving in ways the engagement software was not primarily designed for. The system is computing a firing solution. The solution keeps shifting because the incoming warhead keeps burning its lateral motor. The officer has rules of engagement, authority thresholds, and a weapon release timeline compressed into a space where human reaction time itself becomes a variable. At Mach 10 terminal speed, the warhead covers roughly 3 kilometers every second. A 2-second delay in the launch authorization chain is 6 kilometers of lost intercept geometry. The kill chain is not just a physics problem, it is a human-machine integration problem operating at timescales that test the limits of both. The engineers know this. The glide phase interceptor, under development by Northrop Grumman, is designed to engage hypersonic threats during the glide phase, earlier in the trajectory, when the engagement geometry is less compressed and the plasma problem is less acute. Space-based tracking sensors in low Earth orbit are being fielded to provide continuous overhead coverage of maneuvering hypersonic threats that exploit gaps in ground-based radar networks. Directed energy weapons theoretically offer a defense with cost per shot measured in electricity rather than millions of dollars per missile. The engineering solutions are in progress, but the carrier is already in the water, already within the Fattah's engagement range, already operating inside a threat envelope that the defense systems protecting it have not yet fully resolved. The aircraft carrier has dominated naval warfare for 8 decades because it solved the problem of projecting air power over distances no other platform could reach. The Gerald R Ford can generate 160 combat sorties per day. It carries 75 aircraft. It runs on nuclear fuel for months without a port visit. No other object in the history of warfare has matched that combination of reach, capacity, and persistence. And somewhere on a mobile launcher, a missile that weighs a fraction of 1% of the Ford's displacement contains a physics problem: post-boost lateral burns, plasma blackout, kill chain latency, magazine arithmetic. That the most expensive naval architecture in human history has not yet fully answered. That is not an argument about outcomes. It is not a statement about who wins any particular conflict. It is a statement about physics. 90 seconds. The plasma sheath doesn't negotiate. The VLS cells don't refill at sea. The post-boost motor fires its lateral burns in programmed sequence, moving the predicted impact point, exhausting the interceptor's divert budget, arriving at the target with residual accuracy. The kill chain has a gap, the magazine has a limit, and the engineering on both sides of this problem is still running.